Research in artificial intelligence takes place mostly at universities and large corporations. But both of these types of institutions have constraints that cause the research to proceed in a certain way. In a university, basic research might be hindered by lack of funding. At a big corporation, the researcher might be encouraged to study a domain that is not squarely in the interest of public good, such as targeted advertising. Oren Etzioni is the CEO of the Allen Institute for Artificial Intelligence, and in this episode we discuss AI research, from the doomful premonitions of Nick Bostrom to the unbridled optimism of Ray Kurzweil, as well as the realities of how AI research actually proceeds. Projects at the Allen Institute are defined and structured to solve problems in an intelligent, scalable fashion, so that engineering can proceed steadily from the local maxima of a problem domain to the global maxima. The Allen Institute seeks to bridge the gap by providing ample funding for open source AI research for the common good. Oren Etzioni is also speaking at the O'Reilly Artificial Intelligence Conference in New York, September 26th through 27th, if you're interested in hearing him talk. Before we get to this episode, a few quick announcements. If you're interested in advertising on Software Engineering Daily, send me an email, jeff@softwareengineeringdaily.com. There are more than 14,000 engineers that listen to Software Engineering Daily on a regular basis, so it's a great place to get your product out into the ears of developers or to advertise available jobs that you might have at your company. Also, if you're an engineer that's looking for an open source project to work on, check out Software Daily at softwaredaily.com. This is an open source news and information site about software. It's being led by Jeff Tribble, a member of the Software Engineering Daily community. You can also check out softwareengineeringdaily.com, which is the website for this podcast. You can find links to the Slack channel, my Twitter account, my email. You can find a link to sign up for our newsletter, Software Weekly. And with that, let's get to today's episode. Getting started with Kubernetes can be a challenge. If you don't know where to start, go to aprenda.com/sedaily. There's an upcoming webinar about installing Kubernetes, as well as an introduction to Minikube, which allows you to run Kubernetes locally. At aprenda.com/sedaily, you can also find past webinars about Kubernetes, covering microservices, persistence, and multiple clusters, as well as the history and origins of Kubernetes. And if you're looking to move to a cloud-native infrastructure platform that works with your existing applications, you should also check out aprenda.com/sedaily. Aprenda provides cloud platform software that works with your existing applications and infrastructure. So whether you're looking for a guide to installing Kubernetes, or you're looking for a platform that will give you access to cloud-native infrastructure that works with your existing applications, check out aprenda.com/sedaily. That's APPRENDA.com/sedaily. Thanks, Aprenda, for being a sponsor of Software Engineering Daily. Now let's get back to this episode. Oren Etzioni is the CEO of the Allen Institute for Artificial Intelligence. Oren, welcome to Software Engineering Daily.
My pleasure to be here.
Yeah, it's great to have you. So the software community has come to a consensus that machine learning is extremely effective. And when a machine learning application becomes polished, we start to call it AI. And we're at this point of fruition where machine learning really works. It's being widely adopted. It's being baked into our everyday applications. Did we get here because of some fundamental technical breakthroughs, or because of evangelism and like a changing narrative about how effective machine learning is?
Well, let me say two things off the bat. The first one is that this has been many years in the making. I like to say that our overnight success has been 30 years in the making. So very much a progression of steps and advances and iterations, as we often find the case to be in software. But the second thing I want to say is it's not quite as elegant and tied up as a bow as you might think. It's true that we're getting increasing success with machine learning and data mining and deep neural networks. But it's also the case that a lot of blood, sweat, and tears has to go into it before it works.
Well, what are the most important technical breakthroughs that have been made recently, in recent years? I mean, obviously, it's been many, many years in the making, but I get the sense that there have been some step change things, even if we've been iteratively trying different things and figuring out what the step change will eventually be.
Absolutely. Well, there are two big things that have happened really in the last 5 years or so. The first one is our incredible ability to store and process data, particularly in the cloud with AWS and so on. So we now often have more data available for these kinds of tasks than ever before, and the ability to course through it quickly. Then the second thing is because of the amount of data and because of the advances, effectively Moore's law, but particularly Moore's law applied to GPUs, the ability to run very complex neural network algorithms and complex neural network algorithms on neural networks with many layers, what's called deep neural networks or deep learning. Those things are relatively new, and they've led to remarkable successes in machine learning applications, including in speech recognition, including in object detection, machine vision. And so the numbers, the error rates on these tasks have plummeted, and that's what's gotten people really excited. And of course, one of the most visible demonstrations was pretty recent, which is we used, or DeepMind, Google DeepMind used deep learning to beat the world champion in Go using a learning program. So all these successes have gotten people very excited.
Yeah, my sense is that the tools of deep learning are what's so useful about them in a really pragmatic fashion is that they're almost a way of form-fitting machine learning to be able to take advantage of these advances in Moore's law that we could have predicted a long time ago. So, it's just fairly these things that we could have predicted. It's not like there was some wonderful breakthrough in machine learning. It was basically the data processing speed and, like you said, the storage abilities caught up to the techniques that we've had all along. So maybe you could tell me if that's true, and tell me how you define that term deep learning.
Sure. So first of all, so we're all on the same page. Deep learning really refers to using a neural network to learn when there's more than 2 or 3 layers in the network. So these algorithms that have been so successful were really invented, 30 or even, depending on how complicated they were, even 60 years ago. And I remember when I was in grad school, and this is embarrassing, but this was in the late 80s. Jeff Hinton was around. I was at Carnegie Mellon, and he was a visiting professor there, and he was talking about these great algorithms. And there was a lot of debate. Will these work? Will more symbolic methods work? And we just didn't know. So the algorithms were around for a long time. What's happened with Moore's law is that in recent years, they've proven themselves that when you get them deep enough, now we have these things with 7, 10, 15, 20 layers deep. And when you give them enough data, the other competitors start dropping out of the race. So, think of it, right? The Olympics are in the air these days. And so think of it, you're running a marathon, and in the first mile, everybody's running, neck to neck. And the same is true 10 miles in. When you're 15 miles in, most of the runners have dropped out, and you look at the runners and they're all deep learning algorithms, and you say, these are the algorithms that are able to go the distance with massive amounts of data and massive amounts of computation in places where other algorithms are saturated. Saturated means they don't improve as you give them more data. right? So that's what's special here.
And most of these, or at least many of these algorithms, fall into the auspice of classification or prediction. What are the limits of these techniques when we're using them for the domains of classification and prediction?
Well, so again, just to make sure that we're all on the same page as far as terminology, mathematically speaking, right, all these algorithms are approximating some function. When that function is binary, meaning, yes or no, 0, 1, we call that classification. So we have a loan application and we need to decide whether it's meritorious or not. Or we have a consonant and we need to decide whether it's B as in boy or P as in Paul. Those kinds of distinctions are is what's called classification. There's also something called regression, where what we're trying to predict is not a binary distinction or classification, but it's a real number. For example, what's the probability that this statement is true or the other statement is true, or what are we predicting the price of this product to be a week from now. So all these sorts of tasks, the deep learning has been quite good at. The places where it has challenges is when you need to make a decision that requires more common sense, more background knowledge, more reasoning. Not everything can be reduced to these, distinctions, yes, no.
Is that yet another question of cramming enough data in, or giving enough processing power? Do you eventually get these characteristics of human reasoning, or whatever it is that these types of classification and prediction algorithms don't capture today?
That's a really great question. So that's something that researchers debate. So I think the folks who believe in concepts like end-to-end learning and scaling deep learning to ultimately have networks that are, as big as the brain, which has, hundreds of billions of neurons and, trillions of connections or synapses. They say, yeah, let's just scale this up. Let's refine the algorithm. Let's give them a lot of data. And that's all we need, end-to-end deep neural network learning. There's others, and I'm in the other camp, who say, wait a minute. First of all, these so-called neural networks, actually the neurons in them are a lot simpler than a neuron in our brain. Our neurons are incredibly complex. And more importantly, it's not enough to emulate the brain at kind of a low, almost hardware level. We really need to have a deeper understanding in a different sense, not deep as in more layers, but an understanding of what's going on. We need to have ways to put knowledge in, right? We're having a conversation and I may be learning things from your questions. You may be learning things from my answers. And those are things that are way beyond what neural networks today can do. The fact of the matter is they can't really even understand a single sentence, let alone learn from a sentence and incorporate that into their mental model. So many of us believe that while this work on classification and advances in deep learning are very exciting, we have a long way to go to achieve human level intelligence.
And I imagine that experience with Geoff Hinton, where you had these other algorithms aside from the deep learning techniques back in the day, that has taught you to reserve judgment without seeing data as to how these things are going to play out.
You're so right about that. I'm as I said, I was in grad school in the '80s, so I'm in my 50s, and let me tell you, when I was young, I knew the right answer to pretty much any question you'd ask me about. Now that I'm older and a little bit wiser and I've kind of seen some things play out, I'm actually less certain than ever about what the right answer is. The only thing that I am certain of is some of the folks you see who really are full of hype about AI, about machine learning, folks like Kurzweil or, people like Nick Bostrom who are really kind of doing fear mongering. I think those folks are are really overstating the case. And frankly, their statements are not backed by any data, right? So they say all kinds of things like the singularity's around the corner or some such thing, but they don't back it up with data. So you have to be suspicious.
I agree with both of those guys have kind of a religious fervor around them. But I see some practicality in both of those extremes. Kurzweil really gets people riled up, and probably that has some cheerleading effect for people at Google who are his acolytes. And then on the other side, Bostrom, I'm with you that he's a little fear-mongery, but then again, the downside risk, if he's right, is essentially infinite. So it doesn't hurt to have a Bostrom or two in the world.
Well, so let's talk about that in more detail. So in the Kurzweil case, I would contrast him to somebody like Jeff Dean, who's very technically deep and is pursuing exciting things, but in a more disciplined way. And let me tell you, right? I know some of the folks who work with him. They're really pumped up. They're excited. He has to turn people away, right? Engineers who want to work on deep learning. So I don't think you have to go to the Kurzweil level to get people excited. People are excited about genuine technical advances. Now, if you go to Bostrom, you make a really interesting point about, well, look, if there's even a chance of 1 in 1,000, then he's right. Then we should think about this. The problem is what's called Pasteur's paradox, right? And it goes something like this. You ask people, do you believe in, God and an everlasting hell? And a lot of people will say, no, I don't think that's going to happen. But then you ask them, look, do you admit that there's a 1 in 1,000, 1 in 1,000,000, let's say 1 in 1,000,000,000,000 chance that that's actually true? And a lot of people will say, look, I can't prove to you that there's no everlasting hell. And they say, aha, then you have to be a religious Catholic or a religious Jew or whatever it is. And say, why? And they say, because look, the disutility, if you're wrong and you're sentenced to an everlasting hell, is infinite. And so if you believe there's even an infinitesimally small probability, just do the expected value calculation, and you have to be a religious person. Now, obviously, that's a paradox, right? That line of reasoning doesn't work. And it doesn't work because when you have infinite disutilities, it distorts the whole equation. That's why it's a paradox. So I think, is it good that we have some folks like Bostrom, and we have his center in Oxford that's thinking about these conceptual and philosophical issues? Absolutely. There's 10, 12 there, and probably as humanity, we could afford to be, have 20, 25 people there. More power to them. They're doing an interesting philosophical analysis. But the thing that I object to is the play that these rather hypothetical ideas that, again, are not backed by science or data, they're philosophical ideas, the play that's gotten in the popular press everywhere, right? You see places like Newsweek, which are frankly, read by people who are not particularly well informed, saying things like AI is around the corner and it's, poised to take over. And this could lead to, Luddites, to anti-technology feelings. It could lead to regulation where regulation is not appropriate. And more than anything, it could lead us to be distracted from what the real issues of AI are. There's plenty of real concerns that we should have. The impact on jobs, the impact on privacy, the ethical issues around self-driving cars, and the kind of, drumbeat of, oh my gosh, AI is an existential risk. We're unleashing the demon is frankly a distraction.
Right. Yeah, I imagine you see that particularly acutely when you're looking at all these problems you could be tackling, and we'll get into these. I mean, projects like being able to answer basic science questions. These are things that are still extremely hard to do, and we're nowhere near even being able to imagine. Oh, how do we keep the demon in the box, as Elon Musk says? We're nowhere near even being able to envision how this type of problem would manifest itself, even if it's a practical concern someplace down the line as X approaches infinity. We have no idea what our programming paradigms are going to be like. We have no idea what our APIs are going to be like. So these things are simply metaphysical discussions, and there's just not any really practicality to it. It sounds like is your position.
That's exactly right. So we ought to have a rational discussion of the costs, the benefits, the probabilities of different situations over the next 5 years, over the next 10, 25 years. If we're talking about things that are maybe 100 or even 1,000 years out, it's really beyond the horizon with which we can predict. So, maybe we ought to be talking about the likelihood that asteroids will strike the Earth. Andrew Ng, who's brilliant professor at Stanford, said that worrying about AI turning evil is like worrying about overpopulation on Mars. It's too early. We haven't even shown that we can get 2 people to Mars in a kind of economically coherent and reasonable fashion. Right? It's confusing science fiction with science, right? In the movie The Martian, we got some people to Mars and then, we left somebody there, kind of like Home Alone by mistake. In real life, A, that's not going to happen, and B, we haven't gotten people to Mars.
Okay, so I'd love to theorize about this stuff all day, but we should talk some about, gravitate towards the discussion of the Allen Institute and what you are working on. So what is the Allen Institute for Artificial Intelligence?
So first and foremost, we're a nonprofit research institute whose our mission is AI for the common good. And what that means is that while we're cognizant of, some of the issues and the risks, we're exploring the part of the equation that frankly has been under-investigated and certainly hasn't gotten enough attention in the media, which is the potential benefits of AI. The most obvious example, not something that we're studying, but it's worth mentioning, is the potential of self-driving cars to reduce accidents. We have 40,000 highway deaths a year, many more people who are injured or, unfortunately maimed in these accidents. And estimates are that we could bring those accidents down by as much as 80% by giving a stronger role to the computers and the machines in driving. And that's something that's already happening today with Tesla, with all kinds of, advanced warning systems on cars. That's a very real thing. Another thing that's much closer to what we do is, what about preventable medical errors? Recent studies show that the third leading cause of death in American hospitals is various kinds of medical errors that could be prevented. The doctors are overworked. The doctors are tired after long shifts, right? They're under a lot of pressure. They make mistakes. They can't keep up with the latest treatments, the latest literature, the latest knowledge about side effects, and mistakes are made and people die. So the way I look at it, we really have a moral imperative to study AI with the goal of saving people's lives. The kinds of projects that we work on is we're going deeper into natural language processing, deeper into building computers that can understand us, that can understand background knowledge, that can ultimately understand scientific papers and help researchers solve super tough scientific problems and ultimately help doctors make fewer mistakes.
So let's talk about the medical example in detail. So there's plenty of podcasts people could go and listen to about the surface level details of this increased human-computer interaction. The radiologist is working in conjunction with the computer to be able to identify tumors faster or whatever faster. Give me a sense of the really deep internal engineering challenges of solving this domain of problems.
I'll do that in a second because it's a great question. But your example of the radiologist just reminded me of just another really important point that I want to highlight. And it's the kind of thing where as soon as I say it, right, your audience who's technical, right, software engineers will say, of course, I get that. But really the discourse about this is not like that. AI technology is often perceived, right, as something that's going to take over. But really the manifestation that we see is a lot more like your radiologist example, where it's helping somebody do a better job at a really important task, like finding out if does this person have cancer or not. So that's
Which, by the way, comes back to what you said earlier about our inability to factor in the human judgment angle at this point.
Exactly. So the most successful radiology systems are going to be a human radiologist who has all kinds of intuitions and experience and can ask questions and so on, working hand in hand with a tireless system that's looked at literally millions of examples to analyze the radiology images. Together, they're going to do better than either alone, and that's the wave of the future. AI enhancing our abilities. I wrote an article said AI is going to empower us, not exterminate us. So then the next question, to go to your question, is okay. Then are you saying, hey, we're in a rose garden and everything is easy and good? No, it turns out that to get there, we have to solve some very hard technical problems. So where we are today is when you define a really narrow classification task, like, okay, does this image depict lung cancer or not? And, maybe what stage is it in? The computers are so good at making those distinctions. What's remarkable is some things that are really easy for people, like understanding a simple sentence. Those things are remarkably hard for the machine. And so what we're working on at the Allen Institute for AI in Seattle, and by the way, I mentioned that because we are hiring engineers. We're 60 people. We have 20 open positions for top-notch engineers and researchers. And by the way, if you're a strong engineer, you don't have to have experience in AI to work with us. We're just looking for super smart, talented people. Sorry, that was a little infomercial there. But with that, in mind, the fact of the matter is, I could give you simple examples of sentences that an 8-year-old will understand and the computer won't.
So is the way that translates to the radiology discussion basically that the same techniques for Google recognizing that a cat is in a picture, those same techniques are quite effective for, 95% of cases of recognizing some common type of cancer or some common type of other malady that would be detectable on an image, some type of image scan, but there's some 5% or 2% that would be obvious to a human that would not be obvious to the computer.
Not quite. So the first part of what you said is exactly right, which is, right, you have those kinds of techniques based on deep learning and machine vision will do a wonderful job making those distinctions. What happens is in a situation where something is out of the ordinary and you have to you have to use more common sense. Let me give you an example. What if suddenly you see two images that are completely identical? Maybe that was error inputting data into the machine. The machine is just going to analyze them, say, here, I'll analyze image at a time. A person would say, wait a minute, something went wrong here. Or what if there's another situation where, there's a smudge on the picture and you just literally can see a smudge. There's all kinds of unusual cases, whereas the computer is the master of taking what's happened in the past, right, and finding the patterns in literally, tens of millions of examples, and then looking at new examples. When there's something out of the ordinary, that's when things fall apart. The computer will never say, hey, wait a minute, let me ask a question. Let's have a chat about this. Let's clarify. And that's why when you have a situation like Go, where literally, right, the board is black and white, both literally and figuratively, when you have all these examples, and all you have to do at the end of the day is make a move, right? Then the computer is going to shine, right? This really an artificial situation. If you think about it, what's amazing is not that AlphaGo beat the world champion. What's amazing is that people can play Go at a high level in the first place, right? It's a game, if you think about it, designed for a machine. But when you have something like a sentence, let me give you a concrete example. Time flies like an arrow is like a famous example in natural language processing. We instantaneously and unconsciously understand that sentence in a certain way. It's the idiom "time flies like an arrow." Well, the computer really struggles with that. First of all, what does it even mean to understand that sentence, right? We need to map that to some internal representation. Well, we're not even sure what that representation should be. Also, there's a ton of ambiguity that we don't think about. What if it's actually an imperative sentence that says, time flies, meaning you, Jeff, should use a stopwatch to measure flies and do it quickly, do it like an arrow. Or what if it means there's a particular species of flies called the time flies, and those kinds of flies are fond of a particular arrow. So time flies like some arrow, right? And there's so many crazy interpretations of this sentence that you and I wouldn't even think of initially, but the computer has to, because the computer doesn't have common sense. And I can give you lots more different examples where when the problem is more ill-structured, more nuanced, when our human experience needs to come to bear, suddenly the computer falls apart. How about conducting a high-quality interview, creating a podcast that's very popular? You can't give that to some neural network because you can't even, create labeled data for it very effectively, right? What are you going to do? Take all the podcasts in the world, feed them to a neural network and say, learn? That doesn't work.
Well, you burst my bubble for the day. That was my entire plan with this podcast.
No, it's the other way around. You've got job security in the sense that it's not the case that in the foreseeable future we can replace you with a machine.
Yeah, I know. There goes my hope of automating away myself, though. Well, anyway, so more seriously, when you're talking about hiring, there's all kinds of places where a machine learning researcher could go these days. You could go to MIT, you could go to Google, you could go to the Allen Institute. What is driving the different machine learning researchers to go in these different directions? When you're interviewing people, when you're bringing people to the Allen Institute, what are you finding are their motivations and what drives them?
Well, I'll tell you what one person that we hired from Google said, and I thought it was really quite brilliant. He said, look, Google has 30,000 very strong engineers, but they don't have 30,000 interesting technical problems. So often what you're working on in one of these bigger companies, whether it's Google or Microsoft, I want to pick on Google, it's a great company, you're still a cog in a very big company. And when people want more of a sense of ownership, more of a kind of broad mandate and purview, just ability to build bigger things, they naturally gravitate to smaller companies, to startups, and so on. That's point number one. Point number two is Jeff Hammerbacher, right, who was the one of the founders of Cloudera and then an early employee at Facebook. He left all that behind, and now he's doing data science at Mount Sinai Hospital in New York, working on using big data and AI techniques to help solve thorny problems about diseases. He said, look, the best minds of my generation are working on getting people to click more frequently on ads, and frankly, that sucks. And now again, I don't want to put anybody down, but I do think that some of us feel like we want the technical work that we do to make the world a better place, not just to contribute to clicking on ads or to the bottom line of some corporation. And people who are sufficiently motivated by that naturally check us out, and we don't have a monopoly on this by any means, but they don't want to work as part of the ad industry, as part of analyzing people's data and then selling them things.
Absolutely. Wealthfront is an automated investing service that saves you time. As an engineer, your time is valuable. If you want to invest, but you don't want to spend significant time evaluating your portfolio and allocating assets, take a look at Wealthfront. Go to wealthfront.com/SEDaily to open an account today and get a special offer for Software Engineering Daily listeners. $15,000 managed for free when you open your account. With traditional investment services, there are many humans in the loop that are doing things that Wealthfront automates away. When you pay the commissions and account fees of these traditional investment services, you're paying for work that could be done by a computer. So don't pay commissions and account fees. Maximize your gains with Wealthfront's Set It and Forget It investment automation. Check out wealthfront.com/SEDaily. It would support Software Engineering Daily, and it would introduce you to the world of automated investing. Wealthfront.com/SEDaily. Thanks to Wealthfront for being a continued sponsor of the show. Now let's get on with the show. My sense, though, is that a place like Google or Microsoft has realized that that is the case, and they have started to give researchers who show a lot of promise essentially infinite latitude. Like, you can, if you're a great researcher, you can go to Google and say, hey, I want to research X. It has no immediate bearing on your bottom line, but you're a company that's interested in moonshots. Maybe this will pan out. Maybe this will be something that turns into your next huge business idea. Is that accurate, or am I just totally off?
No, you're not off at all. That's a very fair point, and you're absolutely right. I was at the University of Washington computer science department for many years. I'm still on the faculty there, and I've had more than 100 students of our students, probably several hundred by now, who've gone to Google and other companies, of course. And there's really a wide variability. And there are some people at Google X or at other places who are working on incredibly innovative things and on moonshot projects. And there are those opportunities. That's not the bulk of what people do, right? Google's got, Gmail and Google Maps and, products to maintain. They do make billions of dollars, with targeted ads, and they have thousands and thousands of engineers supporting that. So I think it's important not to confuse what most people there are doing with what some people there are getting to do. But it is absolutely the case that particularly at Google, but at any of these places, there are some people who are working on incredibly cool things with incredibly cool data sets. If you want to build the future of cloud infrastructure and dealing with mind-boggling amounts of data, right? Being at AWS, in Seattle at Amazon is a fantastic opportunity. And the same with, the cloud infrastructures at the other companies. We don't have a monopoly on the exciting problems. I do think that in terms of cutting edge work in AI and cutting edge work that's directly aimed at AI for the common good, we have a great place to work. But we're definitely not the only game, even in Seattle, let alone in the world.
I think that's absolutely true. Sometimes I flip through the recent research papers that have been published by companies, Microsoft, Google, whatever, and there is a lot of research about ads, about improving the click-through rate on some specific type of advertising. It's like, yeah, I don't know. Anyway, but so research for the common good is. How does this differ from the type of research that gets done at an academic institution? Is there more latitude? Because I see some people I know who are in academia, and obviously great stuff comes out of academia. But in contrast with a place like the Allen Institute, it does sound like there is a degree of cruft that comes with the traditions of academia that would just significantly drag down your ability to move fast. Do you think that's an accurate contrast with a place like the Allen Institute?
Well, here's how I would describe the contrast. Again, having spent most of my career at universities, I am partial to them, and of course, we have to remember that companies like Google or Facebook and many others came out of university. Right? They were spun out of, in Google's case, research, in Mark Zuckerberg's case at Harvard, kind of informal research on how to meet girls, what have you. The biggest difference is that at universities, it's really what's called curiosity-driven research, right? It's all over the map. Amazing things can happen, but of course, often they don't. And you typically have one or two people, maybe a graduate student and his or her advisor, working on a problem. That's only you can only go so far. At the Allen Institute, we're working on 4 or 5 grand challenge problems, and we have teams that are bigger, teams of 10 to 15 people, often broken into sub-teams that are smaller, but those teams are working together towards a grand challenge, whether that is developing sufficiently powerful natural language processing so we can build programs that can answer scientific questions and pass the 8th grade science test or the SATs, to programs like Semantic Scholar, where we're trying to use AI to combat information overload. And as I said, ultimately help medical researchers and doctors do better research, make better decisions, and ultimately save lives. So to do those things, you do need bigger teams. You do need more sustained investment. Often the code at universities, right? It's rapid prototyping. You write a quick prototype, you do an experiment, you publish your paper, and you move on. That's the right thing to do in academia. But if you want to go further, here's the famous African saying: if you want to move fast, go alone. If you want to go far, go together. Right. So at the biggest contrast between the Allen Institute and what happens at universities is that we're trying to go further. And we believe the way to do that is to go together, to have these stronger teams. The other point, of course, is as a professor, there is a lot of stuff you have to deal with, which is a distraction, particularly grant writing. Nobody in the entire planet, I've never met anybody, in 25 years as a professor who liked writing grants. You write them, they get rejected, you have to rewrite them, eventually they get funded, but the research sponsor wants you to do something else. At the Allen Institute, we have a huge privilege, which we're backed by Paul Allen, who's had a passion for this field for decades, and his marching orders to us is go have a major impact. And I know that takes time. I know that a breakthrough takes time. I'm going to back you. So that's a huge luxury.
You mentioned something really interesting there. It sounds like these problems that are being solved at the Allen Institute, and you've got these listed on the website. Some of these problems you're working on, for example, Aristo. This is an effort to answer basic science questions like 8th grade biology questions. You've got Semantic Scholar, which is a literature search engine that indexes scientific research papers. You've got Plato, which is extracting knowledge from images and diagrams and videos. It sounds like what you're trying to do with each of these projects is you take a really big problem, a really big canonical problem in machine learning, and then you find a base case of that problem that that feels more approachable. And the sense is that by attacking the base case, you're going to make meaningful progress towards solving the canonical machine learning problem. Is that accurate?
Jeff, that's really a great articulation. I have to say, if this podcast thing does not work out, we should talk about. We need somebody to help us craft this. But you said
I've heard I'm good at marketing.
You are. So you've really said it brilliantly. The issue is, how can we tell if we're making progress? And given that there's so many problems, technical puzzles, research possibilities, how can we assess both for ourselves and for others if we're making progress. And so what we've done is we've identified problems like, say, an 8th grade science test where there's a graduated scale, and we can measure ourselves and exhort ourselves to keep making forward progress. And we try different things, and we iterate through algorithms and through data sets like everybody else. But we've been very proud that over the last 3 years or so, we've been able to continually raise the scores on things. And really, this methodology is relatively unique. We're trying to bring together the best of academia, which is informal brainstorming, creative research, smart people working together with minimal hierarchy, minimal BS, with some of the best things from industry, which is, more professionalism around our software, around our architecture than what, the average grad student can muster, and a clear set of metrics and goals so that we can track and make progress on.
So can you give me an example of one of those projects, and what is the short-term goal of the project and what is the long-term goal of the project?
Sure. So I'll give you 2 examples. The first one, which again is really easy, is in the case of this 8th grade science test or these SATs, where we have these goals, we have annual goals of scores that we want to exceed. Those are benchmark tasks, right? There's no, kind of like a hardware, spec mark for a chip. It's not that we necessarily want, that this will be a huge thing if a computer program can do well on 8th grade science test. Is that we believe that in order to do that, we're going to have to solve difficult problems in natural language processing, in vision, in machine learning, et cetera, et cetera. So here in this case, the metric is really serving as a benchmark, as a score. In the case of Semantic Scholar, which is our program, by the way, is available free of charge. Anybody who wants to use it at semanticscholar.org. That program, we've invested a lot into building what we think is the best search tool for computer science academic papers, and we're broadening, to neuroscience and to other areas of biology. Right, we're heading in that direction. But we don't want to build a white elephant. We don't want to build a tool that we're in love with, has all kinds of fancy bells and whistles using AI, but nobody uses it. So we've challenged ourselves with traffic goals to say, look, if this thing is so great, if AI really helps you in the search, people should start using this. And our goal for this year was to have at least 500,000 people check it out. And we're very proud that we've already exceeded, we have over 1 million visitors who've come to the site, even though it's currently just computer science papers. And the number of repeat users keeps going up as well as people find value in it. And that also forces us to ask the hard questions. Okay, how do we get to 10 million users? What is it that people really need in the search tool, not just what we feel like putting in there?
So, it really sounds like you have a focus on key performance indicators for these different projects. And it makes me curious about how management of the Institute differs from management of your different companies. You've started several companies, for listeners who don't know. In what ways does managing the AI Institute differ from the management of the companies that you've started?
Well, in a couple of important ways, and I have had the privilege to start a few companies, particularly in the kind of e-commerce space. And I should point out, though, all those companies were always on the side of consumers. They're always ones that were trying to find a better price for consumers. We had the first comparison shopping search engine back in the mid 90s, or ones that tell you when to buy your airline tickets so that the airlines don't trick you into overpaying. So I have always been kind of a little bit on the side of the underdog. I think one of the biggest differences is that when you have a startup, until a very late stage, you're always raising money for the next 12 and most 18 months, right? It doesn't make sense to raise more than that because your valuation should keep increasing. And that does put you on a roller coaster ride, right? You set ambitious goals, money starts to run out, you're looking for the next funding round. Sometimes that can cause major shift in direction. It's pretty nerve-wracking. It's pretty exciting too, but it's definitely a roller coaster ride. Here, because we're backed by Paul Allen and he has this long-term vision, we're not on a roller coaster ride. We have ambitious goals, as we talked about in metrics, but we're not on that kind of roller coaster ride of constantly seeking funding and potentially radically changing direction or having to be acquired or acqui-hired because some assumptions didn't work out. That's one thing. And then the second thing, of course, as a startup, right, you have to have a business model. That's often one of the trickiest things. We've built in the various companies I've been involved with very, very cool products where users really love them. But the challenge was, how do you get users to pay for them? And most of us are reluctant, right, to part with our wallet and pay even $5.99 for some piece of software. And so the search for a business model can often be challenging, and sometimes even though you have a great product, you don't have a great business model. Again, at AI2, because we're a nonprofit, we explicitly say ahead of time, we're not trying to find a business model. What we're trying to do is have impact on the technology and make the world a better place. And, having done the other one for, more than 20 years, frankly, it's a relief not to worry about that and just focus on the intellectual content, on the technical problems. So I really try to create an environment for kind of the younger and, at this point, smarter, more technical people on the team that we have, to just shield them from distraction as much as possible and say, let's go, do what you're best at, and don't worry about all that other stuff.
So, and Paul Allen has started a number of these institutes. I know of at least two, the AI Institute and the Institute for Brain Science. Does he have some overlapping mission between these different organizations, the Brain Science Institute being more biologically focused?
So he is a tremendous visionary, and he signed the Warren Buffett Pledge, which means that he's committed to giving away billions and billions of dollars, and he's done that with Ebola. He's done that, in fighting homelessness. But a key part of his vision, as you said, is to create a series of scientific research institute. There's the Allen Institute for Brain Science, and it's broadened its scope. We call ourselves AI2, both because we're the Allen Institute for Artificial Intelligence, or AI, but also because we were number 2. And since we were founded, there's already the Allen Institute for Cell Research, number 3. So, and he's continuing to grow that kind of set of research institutes. In the case of the brain science one and ours, he's been, fascinated with the questions of how do we figure out intelligence. And in some sense, when you think at the very high level, he's kind of hedging his bets. He says, well, there's this methodology of neuroscience, which is in some sense investigating the hardware, right? Really looking at the brain very closely at a subcellular level. And then there's this more software methodology. Nobody knows which is the right one. Why don't I, try to back high quality institutes in each and make sure that they talk to each other? So the CEO of the Allen Institute for Brain Science is on our board of directors. We often talk to Christoph Koch, who's their chief scientist. We're exploring where there's potential synergies as well.
And what is your sense for where that border is going? Like, where are we going to find, or what are we going to find at that interface between the human brain and the systems we use to interface with it? Like, as a machine learning researcher, if you're trying to build systems with reasoning as robust as a human, is it practical to assume that the human brain is always just going to be this black box beyond some level of abstraction? We should just try to find where the border of that black box is and then just figure out some virtual machine that satisfies the characteristics of that black box. It just seems like we're never going to actually figure out the depth of the human brain, and therefore we should try to figure out like where is the minimum border that we can define so that we can make an interface over that border. I don't know. Maybe you could. That's a jumble of thoughts there, but maybe you could tell me what you think we're going to find at this interface.
Right. Well, again, I like to say never say never. I don't know if we'll never understand the brain, but you're absolutely right. Your intuition that this is a long road is a very good intuition. And if you look at the questions, and just like us, they have their own metrics and their own roadmaps. And if you look at what they're predicting they'll discover in the next 5 years and the next 10 years, it's still very basic, almost you might call them geographic questions. What is this cell type, and what does this brain region do? And what is really kind of a map even of the human brain? Very, very basic things. An analogy would be, imagine that we took a laptop and we sent it, back, I don't know, to the 19th century. And people, or maybe lots of laptops, and people were trying to figure them out by really looking at the chip level and at the wire level and trying to kind of measure electrical pulses in different areas. That's a level of abstraction that can tell you something, but it's not the whole story. So there is an analogy there, and there is a concern that looking at things at the very low level is challenging. What the good news would be is if we were able to generate some constraints from the study of artificial intelligence, they were able to generate some constraints from the study of the brain, and we're able to put the pieces together and come up with better, faster progress towards an understanding of intelligence. I love to give the analogy to when we as humans were first studying flight. And some people said, look, we got to build a bird. Let's study how birds flap their wings and are very light. And that's what we're going to do. And other people said, no, we're going to focus on airplanes with fixed wings, right? And that technology ultimately, after many, false turns, tended to win out. And of course, that technology was based on aerodynamics and things like, the Bernoulli principle. So from all these studies that emerged some general principles of flight and of motion that were extremely important. We haven't yet discovered the Bernoulli principle of intelligence. We still don't understand some very, very basic things. And that's why we're still in the early days of these fields, and the different methodologies are all doing their best.
And to what degree is this analogous to how deep learning algorithms develop? Because my sense, I'm not a deep learning expert, my sense is that oftentimes these algorithms, the way that they develop is we don't know why they work as effectively as they do. We just know that they are effective. But is that analogous to this model of drawing constraints for the human brain and then drawing constraints for the machine learning model and fitting those constraints together?
At a very, very high level, yes. But if you look at the day-to-day research, and we certainly have plenty of people here who are working on neural networks and deep learning, often the questions that are investigated are mathematical, about, hyperparameter optimization, or they're software engineering questions. How do we build a, good toolkit to experiment with different things? They're about particular technical aspects that have to do with the particular neural network. Do we use a softmax here? Do we do pooling here? How do we do regularization? I'm throwing a bunch of jargon there, but these are, various statistical questions or kind of almost, black art questions of the craft of these particular tools. it's not the case that people are saying, I'm trying to, raise my performance on this task by 10%. Oh, I know. Let me take this idea that's, you find in the brain of monkeys. That's not how it works. It's just,
right.
Those are just still too far apart.
Right. So we've done a bunch of shows about software architecture, how to scale a typical application. We've also done shows about machine learning. What is at the intersection of those two things? What makes scaling a production application that heavily uses machine learning, what makes that difficult?
Well, the most difficult thing is the fact that even with these neural networks, most of the decisions, most of the work is still human engineering. So when AlphaGo won, or when AlphaGo was winning in the match, and some reporters asked me, what do you think of all this? I pointed out to them that this is not man against machine. This is a team of brilliant software engineers and researchers at Google DeepMind against a brilliant Go player named Lee Sedol. The hardest thing is the fact that quote unquote machine learning is 99% human manual engineering. And even with neural networks, they say, okay, you're doing less feature engineering. You're building less of the representation by hand. That's true, but you're still doing network engineering. You're still choosing how many layers and which architecture. And are you using, an LSTM or not? And I don't want to throw a bunch of jargon, but there are many, many architectural decisions and algorithmic decisions and representational decisions that are ultimately made by the human engineer in any of these quote unquote machine learning applications. And for that reason, that's why it takes years to field a new machine learning application. And that's why we need better software tools to facilitate that process.
Mm-hmm. What are the tools that you're using these days mostly? Is it scikit-learn or TensorFlow?
Oh, so in the case of deep learning, a lot of people are using TensorFlow at the same time, right? There's plenty in Vision, right? People are also using Torch and other thing. It's really a grab bag. And again, it's a little bit, are you using Java or using C++ or using Scala? We actually, our main programming language is Scala. You can get the job done in any of these languages pretty much. It's in part a question of taste. And again, I hope I'm not offending anybody who's a complete, aficionado of one language or another. I think most people will recognize, okay, this may be my favorite language and it's got some features. It's also got some drawbacks and you can get the job done. Right. And of course, Turing universality and all these things tell you that, of course, mathematically speaking, you can definitely get the job done in any language. In the case of non-neural networks, natural language processing, we have our own homebrewed tools. We've actually released an open source project called Ike, which is an interactive knowledge extraction tool that we developed. And at the same time, we rely on, Stanford NLP. They have a very strong open source project. I would say that the biggest thing I can tell you is that A, we're in Scala. B, we do sit on top of AWS, which we found very helpful. And C, that we use open source projects whenever we can, obviously, because then we're effectively collaborating with the community.
Okay, Oren, well, this has been a real treat. Thanks for coming on to Software Engineering Daily.
It's been a real pleasure. I appreciate the questions, and I hope everybody checks out Semantic Scholar and considers a job at the Allen Institute of AI, allenai.org in Seattle. Thank you very much, Jeff, for the opportunity.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphano.com/sedaily. That's symphono.com/sedaily. Thanks again, Symphano.
Wow!